So here's a simple physics question for you. How fast is this object moving? Well, it's pretty simple to say that its velocity in a linear sense is zero. Its average velocity is zero because the center of mass is not going anywhere. On the other hand, you can clearly see that this object is moving. We see kinetic energy. And so because of that, today we need to talk about the idea of angular velocity. Well, aloha everyone. Today we're going to talk about angular velocity and acceleration. So what is this idea of angular velocity and acceleration? Well, it's when something turns or when something rotates, instead of talking about how fast it's going in a linear sense, in meters per second, it makes much more sense to talk about how fast its angle is changing, how fast its orientation is changing. And so because of that, we have something that we call angular velocity. We're going to use the letter lowercase omega, which kind of looks like a rounded W shape. And so this is lowercase omega. It's a Greek letter. And angular velocity is going to be equal to, well, it's the change in angular position divided by the change in time. So what this means is that we're talking about how much the angle has changed in a certain amount of time. And it's pretty simple. If you look at this, the units for this should end up being radians per second. Well, normally that's what we use most in physics. You're probably also going to find anything with an angle over anything with a time. So it could be anything like degrees per minute. Rotations per minute is a pretty common one. You could have, I don't know, something like degrees per hour. Anything that tells you how much it's changing in an angle in a certain amount of time. So let's take, for example, let's imagine, I don't know, something like a wheel. So here is a wheel. And this wheel starts off here, and it is going to rotate. Maybe it rotates over here, and such that this line ends up over here at the end. So it's rotated a angle of 180 degrees, or maybe we call that pi radians. That is going to be the angle it changes. So delta theta is equal to pi radians. And the reason we put a delta there is because we don't care about the exact orientation of it. We care about how much that orientation has changed. Here we can see the change is 180 degrees. Okay, so we have that, and maybe the time it takes to do this is 3 seconds. And I want to know what is the angular velocity. So it's pretty simple to figure out. Omega is equal to delta theta over delta t. This is equal to, our change in our angle was 180 degrees, or pi radians. So pi radians divided by time is 3 seconds. So it's pi over 3 radians per second. And that is our angular velocity. Sometimes we're going to calculate that in terms of pi, but a lot of times we just leave it in terms of pi. So if you know pi over 3, that's going to be a third of this 180 degree angle, which is about 60 degrees every second. So this thing is rotating at pi over 3 degrees every second, assuming it's moving at a constant speed. Just like we have angular velocity, we also have angular acceleration, the ability of this object to change how fast it's moving. For instance, if I put my finger on this to slow it down, we can see it slows down and comes to a stop. That is angular acceleration, a change in the angular velocity. So just like there's an idea of angular velocity, there's also something that we call angular acceleration. Something can speed up or slow down how fast it's turning. And that is going to be given by the letter alpha. Alpha looks like a fish, but it's not fish, it's alpha. So this alpha symbol is a Greek letter, and it is going to be angular acceleration. And remember, linear acceleration was about speeding up, slowing down, or changing direction along a line. Here we're talking about as you're rotating, speeding up, slowing down, or changing direction. So because of that, angular acceleration, we are going to define it as alpha is equal to a change in angular velocity over a change in time. So this is equal to, maybe you'll write it as omega final minus omega initial divided by t. So a lot of times we'll do it using either of these ways of expressing the change in omega. Sometimes if we're given the initial and the final, we'll plug those straight into the right side of this equation. If we're given the change, we'll plug that right into the middle of the equation, and we'll figure out what the angular acceleration is. So take for instance, let's say a wheel starts from a stop. And accelerates to a final angular velocity of 1 rotation per second. What is... Oh, and let's talk about how long it takes to do that. It takes about 5 seconds. What is the angular acceleration? Well, in order to find this, we are going to say that in order to find angular acceleration, alpha is equal to omega final minus omega initial divided by time. So this is equal to omega final is going to be, well, it says 1 rotation per second, which is really 2 pi radians per second, because 2 pi is 1 rotation, right? Minus, well, it starts from a stop, so that's 0 radians per second, divided by, it took 5 seconds to do this. So 2 pi minus 0 is 2 pi, divided by 5 seconds is going to be 2 pi over 5 radians per second per second. So you're probably starting to see a lot of similarities between our regular ideas of velocity and acceleration, linear velocity and acceleration, and our angular system of velocity and acceleration. In fact, there's a lot more parallels than you think. So remember, we have d for displacement. Over here on the angular side, so this is linear, and this is angular. We have theta to represent angular displacement. We have v, vector, velocity, and we have angular velocity, which is also a vector. We have acceleration. We have angular acceleration. Maybe you might have a v final, or a v initial, or a v average. Well, it turns out you would have all of those over here under omega final, or omega initial, or maybe you have an omega average. So it turns out there's a lot of similarities. And when we start writing the formulas, you'll see that there's a lot of the same here as well. So what does that mean? That means we have omega is equal to theta. Wait, I'm putting that in the wrong column. Try that again. V is equal to d over t. Remember that one? Displacement over time, and that's V average. Well, omega average is equal to, it's a vector, theta. Maybe change in theta over time. We'll put it over time, like that. We have acceleration is equal to V final minus V initial divided by time. In the angular system, we have omega, alpha. Alpha is equal to omega final minus omega initial divided by time. So you can see that there's a lot of parallels and a lot of similarities. So it turns out the kinematic equations are also going to have a lot of similarity. You might remember this one as your first kinematic equation that we very rarely talk about. It's the one that said your distance that you travel, or your displacement, is equal to, it is V initial plus V final over 2 times time. Well, it turns out there is an equivalent kinematic equation. That is going to say this. Theta, the angular displacement, is equal to omega initial plus omega final, that was an F, divided by 2 times the time. You might remember our second kinematic equation. That second kinematic equation said this. V final equals V initial plus A times T. Now I'm kind of missing some of my vector signs here. I'm going to go back and put some of those in. Okay, V final is V initial plus A times T. Well, the same thing is true over here in the angular system. Omega final equals omega initial plus alpha times T. The third kinematic equation looked like this. D equals VI T plus 1/2 AT squared. For the third one over here, we get theta equals omega initial times T plus 1/2 alpha T squared. It's not a very good alpha. Let me see if I can do that again. Alpha T squared. There we go. And finally, you might remember this last kinematic equation. V final squared equals V initial squared plus 2AD. Vector, 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 and vector. Well, guess what? There's an equivalent one of that one too. And it looks like this. Omega final squared equals omega initial squared plus 2 alpha theta. So it turns out anytime you would have used a kinematic equation in a linear system, there's a corresponding kinematic equation in the angular system. So the steps are going to be exactly the same. Figure out what you have, figure out what you're missing, and then pick an equation that is only missing one of those variables. Remember, there are 4 kinematic equations. In order to determine, you need to know 3 of them, 3 of the kinematic variables, in order to determine the other 2, which leaves one happy physics student. All right, so that's really all there is to it as far as angular velocity and angular acceleration go. Mahalo for watching, and see you next time.